Welcome back, complex students. The topic for today is analytic functions. So we have a slew of definitions to go through real quick. The first one is, if we take D to be just an open set in the complex plane, then we're going to say F is analytic on D to mean that F prime of Z exists at every point in that set D. And then when we talk about a function being analytic at a point Z naught, that's going to mean that the derivative F prime of Z exists for every Z in some neighborhood of Z naught. So analytic is kind of like differentiability, right? But it's more than just differentiable at a point. When you say the function's analytic at a point, it really means that it's just differentiable on an entire neighborhood of that point. And we've seen examples of functions that are just differentiable at a single point, and those kind of functions are very degenerate. So analytic functions are the good ones that don't act so crazy. Another thing is, if we have some set that's not open, in that first definition, the set D had to be an open set when we defined F to be analytic on D. But if we had some non-open set, let's say E, then we'd say F is analytic on that possibly non-open set. If there's an even bigger open set U that contains E, where F is analytic on that open set. And then the last definition here is that we say F is entire if it's analytic on the entire complex plane. So that just means essentially the function's differentiable at every point in the complex plane. This little note here, so we say if we know F is analytic on an open set D, then that means that F would have to be analytic at every point in D. That's not the definition of analytic, right? I mean, to say F is analytic on an open set D just means that the derivative exists at every point in that set. It doesn't mean that the function is, and doesn't mean by definition that the function is just analytic at each point in that set D. But if it's analytic on an open set D, and if you took an arbitrary point in that set D, then because it's an open set, there exists an entire neighborhood around that point that stays inside that set. So that means, but because the function is analytic on D, it means it's differentiable at all the points in that set. So it'd be differentiable on that little neighborhood of that point. And so that's why F would have to be analytic at every point in the set D. So just a few examples. We know that polynomial functions are everywhere differentiable. Well, then we can say from that polynomial functions are entire. And next, let's think about this function f of z equals 1 over z. In a previous example, we showed that this function is differentiable for any z not equal to 0. We know f prime of z, in fact, is equal to, we worked it out, that it's negative 1 over z squared. We used the Cauchy-Riemann equations to get that, although you can get it from the definition of derivative as well. So we know when z is not equal to 0, the derivative is negative 1 over z squared. And we know f prime of z does not exist, or f prime of 0 does not exist. So from this, we know that f is analytic on the set D equals c minus the origin. And further, if we took any point away from the origin, we could always find a little neighborhood around it that misses the origin. And so we know that at each point not equal to 0, the function is analytic at that point as well. But we already mentioned that if the function is analytic on a set, then it's analytic on an open set, then it's analytic at every point in the open set. And our set D here is an open set, turns out. And then this last example, the modulus of z squared. So in a previous example, we showed f prime of 0 was equal to 0, and f prime of z just does not exist when z is not equal to 0. So this is a very degenerate function. It does have a derivative, though, at 0, but we can't say that this function is analytic at 0, because to be analytic at 0, it would need to have a whole neighborhood around 0 where it is differentiable, but it's not. It's only differentiable at that one point. So f here is nowhere analytic, not even at 0. So just differentiability at a point is not enough to say that it's analytic at the point. So I guess, the moral of the story is analytic is just differentiable on a neighborhood. All right, so let's make a few observations about analytic functions. Well, one thing we can say is that if f is analytic on a set D, we know it's differentiable at every point in that set D, D here being an open set. So if f is analytic on D, then we know that f is continuous on D, because we know differentiability implies continuity. Another thing we know One of our theorems told us that when we know the derivative exists, then we know the Cauchy-Riemann equations are satisfied. So if f is analytic on D, that means it's differentiable at each point in D, and then at each of those points, the Cauchy-Riemann equations must hold by that one theorem that we discussed earlier. So we know the Cauchy-Riemann equations hold on D. And then we had the one theorem that said if the function is differentiable at the point and it's defined on a neighborhood of the point, then the Cauchy-Riemann equations hold. But we had a sufficient conditions theorem also that said, well, if the function's defined on a neighborhood of the point, and we know that the partial derivatives of the component functions of the function exist on a neighborhood of that point, and then they're also continuous on a neighborhood of that point, then we know that the Cauchy-Riemann equations hold true. Oh, and if we assume that the Cauchy-Riemann equations hold true, so we assume all that stuff, then we know the function's differentiable at the point. The sufficient conditions for differentiability on the set D just are tantamount to saying that the function is analytic on D. I mean, the implication from right to left is clear from the theorem that said differentiability implies Cauchy-Riemann, but going the other way, that's just what it means to have a derivative. So if we have two functions that we know are analytic, then we know that things like the sum, the product, and the ratio are analytic on D. I guess with the quotient f minus g, as long as g is not equal to 0 on D. We don't want to divide by 0 there. But we had a theorem that said if you have two functions that are differentiable, then their sum, their product, and their quotients are differentiable. And we had rules for what the derivatives would equal. But we have existence of derivatives, and this happens at every point in the domain D. So if f and g are analytic on D, then so are the sum, product, and quotient. They're analytic on D. And then the last one is just saying, hey, if you got f is analytic on a domain D and g is analytic on some set E where the image of D lies inside of E, then we can use the chain rule. And it tells us that the composition is differentiable on the set D. So here this would tell us that G composed with f the other way around. G composed with f is differentiable or is analytic on D. So using the chain rule here, I guess the point is we're taking all these theorems that we had previously that said if the function is differentiable at some point, then we know something else happens. And we're just extending that to, if it's differentiable on a whole set, then that's telling us it's really analytic on that set. And so we can use the language of, using the word analytic for all these other, we basically can change all those theorems into a statement about the function being analytic on a set rather than just differentiable at a point. So you can kind of think of analyticity as just differentiability, but it comes with a whole set attached to it rather than just at a point. All right, so here is a theorem that I don't think you'll find the result of to be terribly surprising, but it's something that is important and we need to prove. The theorem says that if you have a function whose derivative is equal to 0 on an entire domain D, then, just like in calculus, when the derivative is equal to 0, the function must be a constant. Now, to prove this back in Calculus 1, you would use the mean value theorem to prove it. I won't go over the details of that, but we don't have a mean value theorem in complex variables, at least yet, that we can make sense of. We'll have to prove it a different way than the method you might have used in calculus class. So let's go through a proof of this. Maybe I can kind of give you a little bit of a big picture before we launch right into the proof. So you may remember the word domain here is a technical word that we defined a while back. So domain D is an open set, and it has the property that any 2 points in that set, P and Q, can be connected by a polygonal line that stays entirely inside that set. So something like this. So a polygonal line is just a bunch of straight line segments that are glued together end to end. So we have D as a domain. It has that property. So sort of what we're going to do is if we're going to argue that if you take any just straight line segment, like say that red one up there, we're going to show that if the derivative is equal to 0 along that line, then the function itself will be constant along that line segment. That'll be our first step. The derivative being equal to 0 on that set D means that the derivative is constant along any straight line segment that stays inside that set. From there, we can get to the function must be constant on the whole set because we could just take 2 arbitrary points, and because they can be connected by a sequence of straight lines, the function would be constant on each of those straight line segments, but those line segments share endpoints, and so whatever the value of the function is at the beginning, say the point P, then it'll have to be the same at the endpoint Q. That's how we're going to go about this. Okay, so to prove this thing about what happens on a single straight line segment, let's start our proof by talking about that. So let P prime be a line segment contained entirely inside of D. And we need to introduce a vector that points in the same direction as P prime. So I don't want to use little u or little v. Let me use capital U, let's say. Let capital U be the vector P prime, and then divide by the magnitude of P prime, that vector. So U is a unit vector in the direction of P prime. So what we're wanting to do is get our hands on the component functions of f, and we want to sort of turn this into a problem from multivariate calculus. What we want to do is get our hands on the component functions of f and then look at what are called the directional derivatives. So let me show you what I'm talking about. So let's let our function little f here, let's break it up into its component functions, u of x comma y plus I times v of x comma y. Let's consider the directional derivative of little u in the direction of this capital U vector, this unit vector that points in the same direction as PQ, or P prime. Well, we have a formula for this actually from multivariate calculus. So d little u ds, s here is the arc length parameter of the line segment that goes from P to P prime. But the way you compute it is like this. You take the gradient of the function u and then you multiply it times the vector big U. You dot product it. So let me say where S is the arc length parameter of the line segment from P to P prime. So since I'm saying it that way, when S is equal to 0, that corresponds to P, right? Like the starting point is P, and then it goes to P prime. You may at this point need to stop and like maybe break out your calculus book and review this a little bit on directional derivatives. But the idea is that, if you have a function like we have little u and little v, they're defined in the plane, you can talk about partial derivatives like u sub x is basically how fast u is changing in the x direction, and u sub y, the partial with respect to y, is how fast the function is changing in the y direction. But what if you want to figure out how fast the function is changing in some other direction? You've got a whole 360 degrees worth of directions you can move in the plane, and so you have this idea of a directional derivative. But it has a really nice way to calculate it, it turns out. So the formula that I have right here in yellow is that formula. It's really easy to compute directional derivatives. You just have to find the gradient of that function, which is just, the vector consisting of the first partial derivatives. We know that f prime of z is equal to 0 on this whole thing d. So we know our function's differentiable. So we know then the Cauchy-Riemann equations are satisfied. So we know f prime, just using shorthand here, is ux plus I times Vx. And we know also, because of the Cauchy-Riemann equations, this is equal to, Vy? Yeah, Vy minus I times Uy. But the derivative is equal to 0, right? So all this is equal to 0, if you want to write 0 plus 0I. So what you can see from all this is that all those partial derivatives are equal to 0, right? Ux equals Uy equals Vx equals Vy. They're all equal to 0. We can go back up there to what that formula in yellow and compute that directional derivative. So the gradient of u dotted with big U. So the gradient of u is just ux comma uy. But we just figured out that ux and ui were both equal to 0. And if you dot the 0 vector with any other vector, you get back just 0. When you just sort of restrict your attention to the function little u along that line segment P to P prime, its derivative is equal to 0. So that means that the function u, it's not changing. It's a constant on that line segment. So this tells me that u, little u, is constant along P prime. And by exactly the same argument, we know v is constant, because we could look at the directional derivative of little v in the direction of that big U. And we know the partials of v are both equal to 0, so we'd get that gradient, the 0 vector, and when we dot it with, it'll end up being the same thing. So similarly, v is constant along p to p prime. So we've just taken the problem about, trying to understand the function f and converted it to a multivariate calculus problem involving directional derivatives. We got the directional derivative was steady 0 for both of the component functions along that line segment p to p prime. So that tells us that both of the component functions are constant, just from appealing to what we know from multivariate calculus. And so then that tells us that f, because f is equal to u plus I times v, is constant along p prime. Now, so to put the final touches on this proof, now let p and q be any 2 points in our domain D. D is a domain, so we know there's this polygonal line that connects p to q. So we know there exist these points. Let's say, let me call them p1, p2, I don't know, maybe there's n of them, up to pn, such that this polygonal line p1, union p1, p2, union all the way up to pn minus 1, pn, union pn q. So this is the polygonal line segment that runs from p to q, like I drew at the very top of the page earlier. And all that stays inside of D. And now, by the argument above, we know f is constant on p1. We know it's constant on p1, p2, etc., all the way up to p and q. So I know that f of the first point p equals f of p1 because f is constant along that first segment. But then I know it's constant along the second segment, so f of p1 equals f of p2, etc., 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 that's equal to f of q. So here what we learned is that f of p equals f of q, and so that says f has to be constant on that set D. Because if you take any 2 points, you always get the same result, right? So that all the function values are equal to one another, so it's a constant function. Kind of a cool proof. I kind of like that one. That previous theorem is pretty important. It'll have the same sort of importance in this class as it had in calculus class. You may remember in calculus class, whenever you look at the antiderivative of a function, when you look at the the indefinite integral of a function, you always end up with a plus c. And the reason is that the reason for the plus c is that theorem that we just talked about. It's because if the derivative of something is equal to 0, then the function has to be constant. In other words, antiderivative of 0 is just an arbitrary constant. So anyway, we'll end up with constants of integration when we're dealing with complex functions too. All right, so this next definition is sort of classify the way in which a function might not be analytic at a point. So if the function is not analytic at some point z0, but for every epsilon, so for every size neighborhood that you would put around z0, there would exist some point in that neighborhood where f is analytic at that point. If that happens, then we say z0 is a singular point of the function f. So the function's not analytic at the point, okay? It could be differentiable at that point, but that just means we just know that the function's not. We know that we definitely don't have a whole neighborhood around z0 where it's differentiable. But we do know that there's a lot of differentiable points sort of densely around that point, because for every epsilon greater than 0, we can always find a nearby point within epsilon of the original point where you do have a whole blob of points where the function is differentiable. So just as a quick example, if you look at f of z equals 1 over z at z equals 0, we know z equals 0 is a singular point. We know that, I can draw a little picture here, we know that the function is not differentiable at 0, but if you take any neighborhood around 0, you can always find a point in that neighborhood, like let's say, here. So here's some z hat, and around z hat I can find a little neighborhood, as long as I make a neighborhood around it that stays away from the origin. So there's my little neighborhood around z hat where the function is differentiable. In other words, so the function is analytic at z hat. And no matter how small you shrink that little outside circle down around 0, you can always find such a little red neighborhood around your point away from 0. There can be situations we'll see later where, like, maybe you got the function and there's like maybe the function isn't defined or is like really bad along this dotted line here. And so you might take some point that's on that dotted line. Well, the function's badly behaved at all the points on that dotted line, and it's not analytic at that point because maybe it's not differentiable at that point, but it's not just that you can just draw a blob around it, like do a deleted neighborhood. Every time you draw a neighborhood around this point, you're going to have this like dotted line that goes through the middle of it where the function's badly behaved. But if you move away from that dotted line on the axis, like to some point there, then you can find a little neighborhood around that where the function's well behaved. So this is the sort of things we'll see a little later. So we can get singular points that sort of happen in a row. On the other hand, z equals 0 is not a singular point for this function f of z equals modulus of z squared. It's true that the function is not analytic at 0, but we can't even find like any other points around 0 where the function is differentiable. So this one's really bad. So we can't even call this point z equals 0 a singular point. A singular point at least has some redeeming qualities, like you can find nearby patches where the function is differentiable. But yeah, this one's just really bad. All right, so maybe we want to look at some specific functions now and think about analyticity. So here's just a standard rational function. The question is, where is it analytic? Well, answering where the function is analytic basically comes down to you're asking, where is it differentiable? But you also, after you think about where it's differentiable, you want to make sure that it's differentiable on entire neighborhoods of those points, not just sort of isolated sort of differentiability points. But when we're talking about a rational function, it's a polynomial divided by a polynomial. And so the only places where it's going to be not differentiable are places where the denominator is equal to 0. So we know it's not differentiable where the denominator is e plus 5 times z squared plus 4 equals 0. So i.e., so z equals negative 5 and I guess plus and minus 2i. But those points are very isolated, right? So if I look at, if I take a point that's not equal to negative 5 or plus or minus 2i, so we get these points like, these are our places where the denominator is equal to 0, so where we have non-differentiability. But as long as you move away from those points, you can always find a neighborhood. So at some point like there, you can always find a neighborhood that's small enough around that point where it misses those red dots, and so the function's going to be differentiable on that little green neighborhood, and so the function's going to be analytic at any z that stays away from those red dots. F is analytic on, we'll see minus, those 3 points, negative 5 and then 2i and negative 2i. And then also we can see that those 3 points are singular points of the function, because while the function's not differentiable at those points, if you take any neighborhood around any one of those points, so it doesn't really matter which one, we'll just pick one here. So take a neighborhood like this around this top, around 2i, you can see that it's differentiable at every other point inside that neighborhood. So it's like differentiable on that deleted neighborhood. So that means that around each of the points in that neighborhood, you can find another little circle that misses the red dot where it is differentiable. So that means that the function, that means that that point is a singular point. So basically, we're answering this question of where it's analytic by just using what we know about differentiability rules. We know how to differentiate a rational function like this. We would just use the quotient rule, and we know that the polynomials are differentiable, so we know how to differentiate the numerator and the denominator. So then by the quotient rule, we know how to differentiate the quotient, and we know that it's differentiable everywhere except for where the denominator is equal to 0. So basically, we're getting the analyticity just by applying what we know about differentiation rules. But we can also get our hands on analyticity by using Cauchy-Riemann. So in this example at the bottom here, we got a function that's broken up into its component pieces, and we can ask, where's it analytic? So in other words, where can we compute the derivative? Well, we've got component functions here, u of xy there, and v of xy here. So we have the sufficient conditions for, how the Cauchy-Riemann equations give you the derivative. Let's just note that u and v are defined everywhere. So hopefully you know that sine x and cosine x both are defined for any x. Now cos y and sinh y, they're defined like, if you haven't seen them before, cos y is just e to the x plus e to the negative x over 2, and sinh of y, hyperbolic sine, is e to the x minus e to the negative x over 2. The functions that you're looking at there, nothing bad can happen with them, right? E to the x can never equal 0. So e to the negative x is defined for every real number. So yeah, no problems with those functions. So they're defined everywhere. And also we know that, you can differentiate sines and cosines, and now you can see that the coshes and the sinches, you can differentiate those as much as you want to. So that tells me that ux, uy, vx, vy exist everywhere and are continuous everywhere. Okay, so then next we can compute ux. So ux is, okay, you take that derivative with respect to x and you get cosine x and then times cos y. You treat cos y as a constant, right? And you notice that if you take the derivative of v with respect to y, it turns out that the derivative of the hyperbolic sine is the hyperbolic cosine. So derivative of sinh is cos. So you get, that's really just vy. And also you can see if you do uy, okay, the derivative of hyperbolic cos is just hyperbolic sinh. So you get sine x and then sinh y. And then, but you'll notice that that's just going to be the negative of v sub x. So if you take v and you differentiate with respect to x, you get negative sine x times sinh y. So if you just take vx by itself, it's the opposite of, it has the opposite sign of u sub y. So we see that the Cauchy-Riemann equations are satisfied everywhere. It's true for every, x and y in the world. So by the sufficient conditions theorem, you come up with a better name for that theorem. We know that f prime exists everywhere, i.e. f is entire, analytic everywhere, it's entire. And we can get the formula for the derivative too. F prime of z is ux plus ivx. Ux plus ivx, which we can just write that down real quick. So that'd be cos x cos y plus I times vx, so that'll be a minus here, minus I times sine x sinh y, and there you go. So point of this example is that because we had this theorem, the sufficient conditions theorem for differentiability that involved the Cauchy-Riemann equations, you can tell if a function's analytic by looking at Cauchy-Riemann. And in this case, we were able to deduce that the function was entire because it was differentiable everywhere. Okay, so we can also start proving some things about functions sort of in more general situations. In this particular example, suppose you got a function, f of z, and it's broken up into its component functions there. And we're going to suppose that the function itself and its conjugate function, so that would be your u of x minus I times v of xy would be the conjugate function. Suppose they're both analytic on a domain. So if you had a function that satisfied that particular of a property, it would turn out that the function would have to be constant. Now the way that we're going to prove that the function is constant is, you may remember the theorem that we proved a little bit ago that said if you can show that a function's derivative is 0 on a domain, then the function has to be constant on the domain. So that's how we're going to go about it. We're going to prove that the function's derivative is equal to 0. And we can do that by thinking about Cauchy-Riemann. So we know f is analytic. So that tells me that Cauchy-Riemann is satisfied on D. So, I've got the ux equals vy and uy equals negative vx on D. But also we know f bar is analytic on D. I should be saying here on D. So I know Cauchy-Riemann is satisfied for it also. Now we have to be a little bit careful with signs since we're looking at f bar here, but f bar is like u minus iv. So I'm going to write that as u plus I times negative v. So you have to think about, when you take the partial of the real component, it needs to equal the partial with respect to y of the imaginary component. But the partial with respect to y of the imaginary component for f bar would be negative vy. And also, if we take the partial of u with the real part of f bar, if we take the partial of it with respect to y, we know it's got to be negative of the partial of the imaginary part with respect to x. So that'd be negative vx. So that equals positive vx, right? So when you put these things together, let me highlight these things. Like the ones that I've got highlighted in yellow here, and then separately the ones that I have highlighted in blue here, we can just add those equations together. So if you add the ones that are in yellow, you get 2 times ux equals 0. And if you add the ones that are in blue, you would get 2 times uy is equal to 0. So this tells me that ux and uy are both equal to 0. And then once I know that ux and uy are equal to 0, that tells me that the vx and the vy are also equal to 0. And so now I can see that f prime, remember f prime is equal to ux plus I times vx. But that's just 0 plus I times 0 now, right? And this is all for all the points on D. And so since f prime is equal to 0, that tells me f is constant by the previous theorem that we did. So that's kind of cool. Here's a similar type of example. Like suppose you've got a function f broken up into its real and imaginary parts, and you're supposing that it's analytic on a domain, but suppose that the modulus of this function is constant on D. We're going to prove that the function itself must be constant. All right, so let's see, how would we prove that? If we suppose that modulus of f of z is just some constant, I should say on D here. If c is equal to 0, then that just tells us that f is equal to 0, and we're done. But if c is not equal to 0, then we had a formula, remember, that z times z conjugate is equal to the modulus of z squared. Because we have modulus of f is equal to c, we would have modulus of f squared equals c squared, which then tells us that f of z times the conjugate function of f is equal to c squared. And then since we know that modulus of f of z is not equal to 0 in the case that we're working on here, then we know that f of z itself is not equal to 0. So we can write f bar of z is equal to c squared over f of z. And what's more is that since f of z is analytic, then f bar of z is analytic, because if you got an analytic function, then of course we could just use the quotient rule here or something to say what the derivative of f bar exists, and it equals whatever you get from the quotient rule. So we know that f bar of z is analytic on this set. Okay, so here's what we have now. We know f is analytic as the hypothesis of the problem, and we know f bar is analytic, and the previous problem said if you know that f and f bar are both analytic on a domain, then the function has to be constant. And so that finishes the proof. So by the previous problem, f is constant on D. So I guess, yeah, that's a little bit more of a surprising result to me. It seems kind of like a pretty powerful method that we just employed to get this sort of very general result. Constant modulus functions have to be constant. Good to know. Okay, one last topic related to analytic functions is the topic of harmonic functions. I'm not sure exactly why these things are called harmonic functions. It probably has to do with some relationship that it has to some physical phenomenon. And these definitely do have some application in physics and engineering, but I'll get to that in a little bit. But let's just get the definition first. So let's start with a domain D. And here we're going to have, just think of D as a regular subset of the ordinary xy plane, okay? Like the real R2 plane. And if we have a real valued function, h, from D to R, so this would be like some function you would have seen in calculus, multivariate calculus, a function that takes two real parameters and gives a real output. So we'd say a function like that is harmonic on D if, one, it's got these, its first and second order partial derivatives exist on D and they're continuous. And a certain equation is satisfied. It's called Laplace's equation. It's the second order partial hxx plus the second order partial hyy. That needs to equal 0. That equation is called Laplace's equation. My very minimal understanding of the physical aspect of this is that I think Laplace's equation describes some sort of equilibrium that the function has on the domain. So if you think about the function evolving over time, it's not changing. It's like you might think about like some sort of like electrical current or something that's happening over some sort of two-dimensional plate, like a two-dimensional domain. Like maybe it's in some state of flux where it's the charges are changing rapidly or something like that. Then that would be an example where Laplace's equation is not satisfied. Or if you thought about some situation where like maybe there's a heat, like some sort of heat source heating a metal plate that's like a flat metal plate, and at first when you start heating the metal plate, like the temperature is going to start changing, But if you just keep like a steady temperature on it from the heat source, eventually the plate will settle out into a steady temperature. And then at that point, it'd be satisfying the Laplace's equation. At least that's my understanding of it, something like that. And so we want to be able to tell if a function is harmonic. So just as a quick example here, here's a function t of xy equals e to the negative y sine of y. I want to show that it's harmonic on basically any domain in the real plane. So basically on the whole real plane. Well, just start computing these partials, right? So you got tx is e to the negative y, cosine x, sorry. And txx would be negative e to the negative y sine of x. And then likewise, let's see, ty is equal to negative e to the negative y sine of x. And tyy would be positive e to the negative y sine of x. And I think it's pretty clear that txx plus tyy, okay, you get 0, right? Because you get negative e to the negative y sine of x plus positive e to the negative y sine of x. That comes out to 0. So, this saying something is harmonic is not really a statement about complex variable stuff. This is something you define about real valued functions. But it's going to have, of course, some relationship to complex valued functions soon. Now you might ask why care about harmonic functions. Well, I mentioned that Laplace's equation has something to do with some sort of like equilibrium state. So maybe to draw a little picture of what might be going on. In this picture below the blue area, think of that as some sort of like metal plate. And it's got some boundary conditions, like maybe on the left and right. So if you took the function that we were talking about in the previous example, this e to the negative y sine of x, if you would put in any multiple of pi for x, you're going to get the sine of a multiple of pi is equal to 0, right? And so in this picture here, those two vertical lines, the first one's at 0 and the second one's at x equals pi, that function t would be equal to 0 identically on those entire vertical lines. So you can imagine that that's like there's some sort of like insulator on the left and right sides of this plate. Now, this plate goes forever, okay? So it's an imaginary plate that extends to infinity, but whatever. And then on the bottom side of it, where y is equal to 0, if you put y equal to 0 into that function up there, you get, e to the negative y is just equal to 1. And so on the bottom side of this thing, the temperature is varying, according to what the x value is. So the temperature sine of x, depending on whatever x you're at. And you can think of that as like some sort of heat source. It's just like this steady heat source along that one side. I'm not saying it's a constant heat source along that whole side. Like at some points on that side, the temperature is going to be hotter than others, but each point is bringing the same amount of heat as you evolve over time. Now, if you'd first turn on the heater on the bottom side according to that heat function, the plate would start heating up, right? But after a time, it would settle out and it would reach some sort of like steady state temperature. The question is, this is so-called Dirichlet problem. Solving the Dirichlet problem in a variety of different scenarios is a big deal in complex analysis. Like if you go on to take more advanced complex analysis, you'll definitely get into the Dirichlet problem. The Dirichlet problem is, it says, let's say that you know what's going on the boundary of some plate. Okay, just some, we're going to come calling it a plate, but it's just a region in the complex plane. Suppose you know what's going on along the boundary. How can you find a harmonic function that tells you what the temperature is on the inside of that plate? And it turns out that as long as you know that the boundary has sort of relatively nice properties, something about being harmonic, then you actually can solve this problem. You can always, just by knowing what's going on along the boundary, you can deduce what's got to be going on in the interior. That's actually a really cool thing. You're taking just the scant information about what's happening along the boundary and you're getting what's going on the inside. It's kind of reminiscent of like Green's theorem back in your multivariate calculus class. With Green's theorem, you could read, if you had a curve that enclosed some boundary in the plane, just by sort of integrating around the boundary of it, you could get what the area of the interior was, which was kind of cool. One last theorem, and then we'll be done with this particular lecture. This last theorem says that if your function f, broken into its component functions, u and v there, is analytic on a domain D, then the u and the v both have to be harmonic on that set. So analytic functions have harmonic component functions. Now to prove this, we actually need to cheat and look ahead a little bit to something that comes later. So it turns out that from the 4th chapter in the book, there's a theorem that guarantees that if f is analytic at a point, then the component functions u and v have continuous partial derivatives of all orders. So you can look at like uxx or uxy or, ux 10 times, like uxxxxxx, that sort of thing. Doesn't matter how deep you want to start doing those partial derivatives, they always exist and they're continuous for an analytic function. So that's a little bit of a cheat, but that's what we need to prove this thing. So then going ahead with this proof with that big assumption. So assuming f is analytic, we know that Cauchy-Riemann equations hold. So we have ux equals vy and uy equals negative vx. And so, that would tell us if we take partials with respect to x of both of these equations, we still get a true equation. So in other words, I'm abusing notation here, but we end up with uxx equals vyx and uyx equals negative vxx. And we can also do the same thing with respect to y. So we get uxy equals vyy and uyy equals negative vxy. So something we'll have to remember from multivariate calculus. So from multivariate calculus, we know if the second order partials are continuous, then the mixed partials are equal. So i.e., we know uxy equals uyx and vyx equals vxy. Using that fact, we end up with, let's see, if we start with this equation right here in yellow, then I know uxx equals vyx, but because mixed partials are equal, that's equal to vxy. And then I just look around and look for a vxy, like, aha, there I see vxy right here. So I can see from that equation that vxy is equal to negative uyy, or in other words, uxx plus uyy equals 0. So u satisfies Laplace's equation. So we get that. And we can do the same thing for v. If we look at vxx, there's an equation that involves vxx right here. I'll do in green. So I know vxx is equal to negative uyx, but mixed partials are equal to one another, so that's the same as negative uxy. I see uxy right here. So then I can see that negative uxy is equal to negative vyy. So again, from there we deduce vxx plus vyy is equal to 0. And that proves it, right? That's what it means for v to be harmonic. So those last two equations that we proved out there gave us that u and v are both harmonic. So analyticity implies harmonic. All right. I think I'll stop there. Talk to you again soon.